Hello everyone, welcome back to Dragonfly Engineering. So we are on part 2 of the Stoker Steam Engine Valve sleeve manufacturing to help out Keilth Rucker at vintagemachinery.org. And if you haven't seen the first in our series, we turned down the ID of this Stoker Steam Engine Valve sleeve on the track CNC lathe over there. And that was a few days ago. And now the next step is to machine all of the steam ports into the valve sleeve itself. And you'll see in the previous episode how Keilth Rucker pressed these valve sleeves out of the Stoker Steam Engine, which is a steam engine we've been working on for a few years, and which offers up coal to a steam locomotive that the Nashville Steam Society is restoring, the steam locomotive 576. I think they're coming along pretty quick with it too, because Keith is telling me we need to get this Stoker steam engine finished. So in this episode, we are going to do the next step, or the second op, at least for my part of this journey with these valve sleeves, and that is to use the 5-axis Haas CNC to machine all of these side steam ports into the valve sleeve itself. And what this valve sleeve does is basically it receives steam into the center with this port right here, this long port from the steam chest and the Stoker steam engine. And then there's a spindle that pushes back and forth, or a valve with 2 rings that basically will port steam through these arrays of holes into the steam engine cylinders. And then as that spindle moves back and forth, it will release the steam out through other ports like these exhaust ports right here. So if you imagine basically a spindle attached to the eccentric on the steam engine drive shaft itself is constantly shuttling back and forth and opening and closing these steam ports and these steam exhaust ports. Down here, the exhaust port is basically just a hemisphere cut. And this whole thing pushes into the engine block of the Stoker steam engine. So there's a distinct pattern that we need to follow for all these ports, because they do match up with the cast-in ports of the engine block itself, the steam engine block itself. And they are also mirror images of each other, which means I had to program basically 2 parts for the 5-axis CNC mill. And we're going to use the Haas UMC 750 basically as a 4-axis mill for almost all of this machining. There is an interesting artifact with these round slots that are spoke, centered on axial spokes that come from the center line of the cylinder, and that it actually creates a 5-axis operation. So you'll see how as this cylinder is turning in the mill, it actually tilts up a little bit just to basically deal with the linear cut that is in a cylinder. It creates like basically a funnel shape on the ends. So you will see the mill lift up a little bit and then come back, but we're mostly using the 5-axis as a 4-axis mill in this episode. And then when we come back, I will load this plastic sewer pipe tube, which is almost the same dimensions as our actual part itself. And I'm going to use this as basically a kind of a wax form or a sacrificial test piece to run the whole program, so that if I find a problem, I don't scrap this part, which now has a lot of work from at least 3 different people in it now. So as you get closer and closer to irreplaceable objects that someone asks you to machine, you really need to run a blank before you actually go live with the real part. So that's what we're going to do. Quick update to this video is that after doing the editing, I discovered it's probably better to make this a 2-part episode, because there's a lot of material covered in the setup, which actually is going to be next, is the probably time lapse of a lot of fixture machining that you can see me do in kind of rapid progression to get to the point where we can fixture this tube into the mill. And after the first episode where we turned the inside diameter, A couple of viewers were curious about the toolpath programming using the Mastercam, which isn't sponsored, by the way, but that's what I use. So there's going to be a separate episode just showing the programming and the setup virtually in the cam system of Mastercam. All right, so enjoy probably the time lapse set to music of a whole lot of fixture making, and this is part 1 of part 2. All right, so here we are over at the Haas UMC 750, and this is a 5-axis milling machine. So we've got a gimbal table which will roll this way, and that creates our fourth and our fifth axis. So it's, a lot of the operation of this mill is when this table is actually spun up 90 degrees from where it's sitting right now. And I did have to do a lot of fixturing to fit Keith's part into this mill. I didn't really have it set up for round stock, especially round vertical stock. So I did get this 4-jaw chuck from Amazon, basically, pretty cheap. And I did have to make an additional aluminum riser block for this mill as well. The thing about, I guess one peeve that I have with the Haas UMC line, at least this version, this is a 2019 Haas 5-axis mill, is that it has very conservative crash avoidance zones in it. And that means that basically your part has to exist like way high off of the table, because when this table rolls 90 degrees, you run a lot of risk of banging the sheet metal housing or other parts of your spindle into features on your table itself. So it really has like this cone of exclusion, which is probably like a 60-degree cone that comes up, or like a 45-degree cone. And if your part is inside of this cone, it just isn't going to let you machine it. It'll say a potential collision detected, and it'll just stop, and you got to restart and lift your part higher up. So that is one of the issues that I have with this particular 5-axis mill. I don't know if they've updated that in the future, but you could also argue that that has saved me and I haven't crashed this mill, because if you roll your table up against your spindle while it's spinning with like 2 tons of force, that's probably going to be very expensive. So it's a love-hate relationship. I hate the fact that I have to have extremely long tools. Let me bring that spindle over. So I'm in the hand jog mode, and we'll bring our center drill over. You can see how long I've got for a tool stick out here, and we'll wait for the plane to pass and I'll get coffee. But there's also basically a big exclusion zone cone with the tool that you have as well. So you need your part to be really high up on the table, and you need your cutting tool to be really hung down low from the spindle flange itself. And then basically those 2 triangles can't overlap, otherwise the mill says potential collision detected, even though in reality your spindle is probably like 6 inches away from the rolled up table, but it still says potential collision. So refixture. Anyway, so that was a little bit of work, and I had to basically use an existing riser plate, which is just an aluminum standoff plate, and then I made this extra riser plate, which used to be an aluminum injection mold plate that I basically repurposed as an additional spacer for the new 4-jaw chuck, which hopefully I can fit on the track lathe that we used last week. And then I additionally had to shim up the part some more, and I made this drawbar to basically pull the part into the jaws and keep our piston sleeve, or our Stoker sleeve, kind of pulled down square onto this chuck. All right, so let's load our plastic part, and we will run the program to trial out to see if there's any problems with our program. And it won't be the end of the world if we break a piece of plastic, but I'd rather not break the mill or Keith's 1-of-1 valve sleeve. And then once I'm happy that everything looks good, then we can load the actual real cast iron part and then let her rip. So this ABS sewer pipe it's about maybe a 1/4 of an inch bigger in diameter than our actual steam valve sleeve. So we'll just open these jaws up like one turn or so, and then we get our part in there. And it was pretty much centered, but this plastic part is oversized anyway. And it's not a big deal if our plastic part is slightly out of coaxial alignment with the zero of the mill, because it's bigger than our part anyway. And the tool travel clearance is higher than the oversized or off-centeredness of this part. Hopefully that made sense. Yeah, I took one machining class at Ohio State University, and they gave you these pieces of wax, and you'd stick your piece of wax in the mill when you're trying to figure out how to machine something. So not much happens when you damage your piece of wax, but you don't want to crash into your fixture either. So I also have some footage of turning this top cap that's got a precision diameter for the steam sheath. And this is our, oh, and then we got this half 13 rod with yet another custom washer that locks underneath the flange of this this four-jaw chuck. So all of that combined is our fixturing for this part, and it still tends to have a little bit of rattle or chatter out here at the end. So, because full disclosure, I already machined one of Keith's parts, and this is the second part, the mirror part. And so we just run the 1/4-inch end mill at a higher RPM at a low feed rate, and we just deal with the fact that this is cantilevered. You can't really get like a tailstock in this 5-axis mill like like an old manual setup would have. All right, so we'll tighten this thing down. And the default center of the mill is in the exact center of rotation of this table. And I've set the tool heights. I actually had to update the depth of this drill center. And we can do that again. We're going to use the tool setter, which is this guy back here in the corner of the mill. And unlike other mills that I use, this thing is a full probing system. So there's a probe that's used to touch off and find your part, as well as the top of your part. And then that same probe is calibrated on this tool setter, which also is used to set all the tool heights. And the distance of that probe is basically offset from all your tools, so that all the zero locations are actually that little pedestal right there in the back of the mill. And this is relatively common for CNC operations, but maybe kind of a new thing for manual milling operations. But I do a combination of both. I still, for most of my 3-axis CNCs, I still touch my tools off from the top of the surface like I'm running a manual mill. But this thing is so crazy with its rolling around and everything that it's impossible. You have to have a tool setter to set your tool heights and your part location and part height, because as soon as we hit go, the first thing that's going to happen is your table's going to move. So, all right, yeah, let's reset that spot drill. So we're on the screen under the offset settings, and right now tool 1 is in the spindle, and you can basically see what the information is. For instance, like the spray coolant position is 11, so you're spraying coolant on your tool tip. Approximate length of that tool is 9.5 inches, and all the way at the end you can do probe type, and we are going to measure the length of this tool, and it gives you options. So we're going to tell it tool offset measure, and then probe selected tool, which is this one, and you've got other options too. And then we can run an MDI, and MDI means manual data input, which is kind of like a quick script screen instead of the full program. And it'll run this little program and measure the length of our tool. So I will hit cycle start, and see how the Haas mill will figure out how tall this tool is from the flange location to the tool tip. And that's needed so we don't drive the tool deeper into our part when it's doing its 5-axis machining. So I'm going to hit cycle start. It goes over to the tool setter. You may see some flashing lights, and there's LED lights that are talking to a receiver in the cabinet. And as soon as it touches, a red light happens, and it'll double check that height and record the tool height on the screen, and that's it. So we just set our tool height. And we do that for all the tools in this setup. Okay, so let me grab the program and we will do a wax run, if you will, on our part. Okay, so I loaded our USB stick and we will go to the memory page, no, list programs. And then we scroll around, I'm just hitting the cursor buttons to the USB stick, and we will find the program called Mirror. And it's in alphabetical order mostly. But here we go. I like to check the time and day that, oh yeah, I made this today and 1 minute ago. And then we will select program. And then our program is loaded in the program preview page. Then we can hit menu to get into the menu page. And I will reduce our rapid speed to 5% and our feed rate to 10%, just to make sure we're all safe when we turn this program on. And as soon as I hit cycle start, we will start, and I will keep my thumb on the, So then we just hit cycle start, and I will be ready on the feed hold if I see any issues. But I'll get the camera set up so you can see what's going on inside. So we got our first tool loaded, so I'm going to hit the cycle start button, and it will get into its clear position. And I've got the rapid slow, but I can speed it up and then slow it back down again by just hitting the override buttons on the controller. And that sound you hear is the tool changer advancing to the next tool after this tool is done cutting. I'll hit feed hold, and we can zoom in. And again, this is just plastic that we're cutting right now. And cycle start. I'm just looking for any kind of funny problems that may happen. I can turn the coolant off, especially since we're cutting plastic. I'm just being real conservative with the feed rate. I'll increase it to 30%. And there we just touched our first drill center point. And then I like to pull the tool out pretty much to 0 on the Z for any extensive motions with the rotary table. And we're looking for things like sometimes with Mastercam, it thinks that the drill and the tool should go through the other side of the part to drill that hole. So if I start to see that this tool is just wanting to plow through the entire cylinder to drill the hole from the backside, then I need to stop it. And that does happen. Sometimes it flips direction of cut on you for no good reason. Now I have actually run the other cylinder, so I do have a good sense that we're not going to be crashing into our lathe chuck. But again, subconsciously I hit the feed hold when I saw the spindle heading towards that chuck at a high rate of speed. So this has kind of already been kind of proofed out with the previous part. But if I'm just cold programming this the first time, I wouldn't be running it this fast to cycle through the first operation. Mostly because like this is my mill, it's not the company's mill. So if I break my mill, I gotta pay to fix it. And so we're drilling a bunch of basically plunge holes so that the 1/4 inch end mill doesn't have to cut on its center so much, because they don't really like to do that. It creates a lot of force. Even though I'm using a center cutting end mill, there's still basically theoretically 0 cut velocity right at the center of the tool. So by drilling out the center web, as it's called, or the metal that holds the flutes together for an end mill, it's a much easier cut when we plunge in to cut out our slots. But we need to cut these center holes so that our drill bit doesn't lead off on this cylindrical face and not actually cut a hole, but just kind of drift off and break off. So now we did a tool change for our first drilling operation. And again, this drill is just to clear out the center of the flutes of our plunge operation for the 1/4 inch end mill. Now when we're done machining this, I'm actually going to pull this piece of plastic off and measure one of the key features relative to the base of our 4-jaw chuck to make sure that I've got the position of the stock correct before we load the real part. You see some of the clearance concerns that I had. Yeah, and I had to position this stock and the tool geometry to interleave with the steps on that 4-jaw that's sitting in this chuck. I slowed down our plunge to 5% here. Now we're going to cut our grooves. Here we're cleaning up the corners with an 1/8 inch end mill. Okay, we are done with our trial part. Now I'll pull this and I'll measure some dimensions compared to the cast iron original sample, the old rusty one. And if everything checks out, then we will run our actual part. Again, I didn't dial in this plastic tube because it's soft and oversized anyway. Okay, let's check it out. All right, so let's check our dimensions based on our original sample. Let's see here. Yes, this is the mirrored part that we're cutting, and this is the one that we just machined. All right, so if I measure the, okay, so when we loaded the plastic, this was against the 4-jaw chuck in the mill. So this is the bottom of the part, and then this is the corresponding bottom. So I'm going to measure this feature on the original part, and we get a distance of 1.172. Okay, so that is this dimension. Then if we look at our new machined part, we get 1.172 as well. Now, you know, this old part was cast, so these were probably, I don't know if these were cored in or machined in, but you know, this part isn't super accurate, 1.175. But the average dimension is, see there we got 1.1715. But on average, we're looking pretty good. See, that's a little high, 1.173, 1.169. So yeah, I think all intent purposes, plus or minus 0.003 is more than adequate for this particular feature. 1.173, 1.173, yeah. So I think we're good. And now what we want to do is make sure that we are cutting the correct handedness, or the mirrored part. So if we have all the steam outlet valves, or inlet valves down on the table, and then we also put all of the same steam valves down on this table, like so, you can see that the steam input port is on the left side, and it's on the left side here. And then this small exhaust port and this small exhaust port are on the same side as well. So that's good. Where the mirrored version of this thing, again with the steam valves down, its exhaust inlet is on the right-hand side, and the little port is also on the right-hand side. So this is the program we're cutting now. I cut this one already, so I think we are set. So I checked our dimension is good, and that we are cutting the right side, or the right hand of this part. Okay, so let's go ahead and load our stock. Oh, and then the small flange is down, so I'm going to load the small flange down as well. So I'll meet you over at the 5-axis, and we will get our stock loaded.